Kia ora team and welcome to another online tutorial. Today we're going to be talking about distance time graphs, how we can use them, what information we can get from them, and what do these lines even mean. I'd like to start out by pointing out that on our y-axis, our axis going up, we have distance. On our x-axis, our axis going across, we have time. Whenever I see a graph like this, team, the first thing I'm going to do is start out by breaking down the graph into its relevant sections. Okay, so I look at where the slopes are similar, where they're different, and I mark them with the dotted line on the graph. Remembering that in a test, on a question, don't be scared to mark the paper. Okay, so if I have a straight line for a section, I'm going to mark it. If I have a curve for a section, I'm going to mark it. Just making sure that I have every different little point marked out. I'm also going to label them. Okay, 1, 2, 3, 4, 5, and 6. Right? Using letters is perfectly fine. I just like to use numbers. So what's happening on a distance time graph and how is it relevant or different in these particular sections? We can look at 1. Okay, we can see that as we go along 1, distance is increasing as we go up in time. So distance is increasing, time is increasing, and it's a flat line. So it's increasing at a constant rate. Okay, so we say that when we have a flat line in a distance time graph that we have a constant velocity. Okay, remembering that V equals d over t, and distance and time are changing for us in these parts equally or constantly, so we have a constant velocity. All right, let's look at point 2. We can see that for us, distance is not increasing. Okay, it's not going further up the y-axis, but it is going further along the time axis. So we have no distance increase, but time is increasing. That means that we're not going anywhere, not moving. So when we see a flat line in a distance time graph, we know that we are stationary, or as they like to call in level 1 mechanics, at rest. Now we can see for section 3 that we got something different. We're no longer increasing our distance and our time at an equal rate. We're also not stationary. We're not just flat. Okay. What we have here is an object that is moving. But if I start out here and draw a tangent, we can see that the distance is starting to increase faster with time. Okay? And if we have something that is moving faster with time or covering more distance as it gets rolling or gets moving, okay, we know we're not moving at a constant velocity and we must be accelerating. Okay? For 4, right, we can see again that we have a flat line, constant velocity, distance is increasing, time is increasing. We know it's straight, so there's no increase in that manner. But looking at 4 and 1, it's steeper than 1 is. Meaning that in the same amount of time, if you took a equal section, right, if we took 3 of these dots across, 1, 2, 3, or 4, okay, 1, 2, 3, 4, the increase is much greater. So it's gone a further distance in the same amount of time, okay? So it's also constant velocity, right? But it's greater, okay? It's going faster. So it's got a greater constant velocity with a constant velocity for 1 being lesser, okay? It's less steep. The steeper the line, the faster it's going. Let's have a look at number 5. It's the opposite of number 3. We can see that 3 is starting to increase in speed as it moves up because it's curving up, whereas 5 is starting to decrease in speed because it's going down. And if we draw a tangent at any given point, we can see the gradient or slope of that line is getting lesser. So if it's still moving, but it's slowing down as it does so, we are going to have deceleration, or we are decelerating. Looking at number 6, we have a flat line, so we know it's also at rest. Another thing we can do, team, with these graphs is that we can, and I'm going to change color here, calculate velocity, okay, by looking at distance, looking at the time taken to go that distance, and calculating velocity, all right? We can also just look at the point at which it is at a given point and where it corresponds on the y-axis, and that'll tell us the distance an object has gone at that given time. So if I picked another one up here and I trace that across, all right? We can see that for a given time, we have gone so far. We can actually calculate acceleration, okay, for a section like 3. If we look at or calculate the velocity of the sections before and after, so if we look at the velocity here, which for us would be 0, and we calculated the velocity of 4 the same way we've done for section 1, we could then look at the change in velocity and divide it by the time taken, okay, which would be this section here, and we'd get our acceleration. Well, team, that's how we use distance time graphs and the information in which we can get off it. Hopefully that's helpful. Hopefully it helps you get out there and get into some level 1 mechanics. Good luck. Have fun.